Hello everyone, this is Tim Pavlak. In today's video I will show how Ansys Workbench Mechanical can be used to achieve an accurate solution to a nonlinear stress problem. Let me show you basically what we're striving for. Here's the first solution that the software will automatically generate for me. Looks reasonably good, but as we'll learn it's not necessarily very accurate. Here's the second solution the software will produce for me, and finally the third solution. This solution that you see here happens to be quite accurate, and we'll learn why in a moment. So let's go back to the initial problem setup. Here I have three plates, actually two plates, and a single rivet holding those plates together. If I hide the rivet, you can see that there's a hole in the rivet, a hole in the plates where the rivet is holding the parts together. Each of these parts in the model are made up of aluminum alloy. And if I switch over and show you the engineering data view, I see that the aluminum alloy has a multilinear isotropic hardening stress-strain curve specified. So that tells the software that the material is nonlinear and it will have to converge a solution for every mesh it's given. Now going back to the model setup, I see also that I've made use of symmetry in this model. The boundary conditions are symmetric, my geometry is symmetric, so as a user I can take advantage of symmetry to lower my computational cost for any solution that I'll perform, and that's indicated by this annotation in the graphics window. The second major nonlinearity in this problem is the fact that I'm modeling the assembly with frictional contact. Here you see frictional contact defined between the top plate and the rivet with a friction coefficient of 0.2. Likewise, there's friction between the two plates and friction between the lower plate and the rivet. Now as a user, I've got this set up. It didn't take much work. I haven't gone through the details here, but it doesn't take much work to set a model like this up. I have not generated a mesh, nor do I have an initial solution. So as a user, I can set the software up to do those automatic edge adaptations for me. The first thing I want to do is insert a convergence object on the result of interest, and I've done so here on the equivalent stress result. And now the software wants me to enter an allowable change. I'll enter 2% allowable change in stress, and then I'll simply ask the software to converge the problem using at most 2 refinement loops. So that means it's going to perform an initial solution and then refine that solution up to 2 times in an attempt to satisfy the 2% change in allowable stress I've specified to the software. At this point, all I have to do is initiate the solution. What the software will do is it will generate a first mesh for me, as you see here in the progress window. We see this first mesh fairly coarse to start with. It's a default mesh. And then it will produce an initial solution on this mesh. Since the simulation is nonlinear, it will take some iterations for this solution to converge. And after that, it will look at that initial solution and then decide where to refine those elements in that initial solution to produce a more accurate solution. And then it will repeat that process a second time until it satisfies the maximum number of refinements I've allowed, or until it achieves the minimum change I've specified. So I'll pause this and then we'll come back and revisit the solution because it takes some time for it to complete. Here we are back after the software has done its work, attempting to converge the nonlinear solutions and converge the edge adaptation, which essentially refines the mesh after each solution to produce a more accurate answer. Here you see the software has done its work. You have very good refinement of the mesh in critical areas, automatically determined by the software. There was no manual intervention on my part. And if I take a look at the model again, you see that the nonlinear behavior is clearly indicated here by the plates separating and the attempt to shear that rivet. Now let's take a more detailed look at the convergence history. Here you see the first solution produced a stress of 528 megapascals, followed by a stress prediction of a maximum of 606 megapascals, and finally 598 megapascals. The percent change in solution is monitored, and that percent change is satisfactory according to the 2% change I've specified. And you also see a record of the number of nodes and elements and a nice chart showing the convergence, the H-adapted convergence. So here we have that final solution. It looks very good, but let's see what the solutions looked like in more detail as we worked up to this point. Here was the initial solution, relatively coarse solution. It's that 528 megapascals. Here's the second refinement. It's refining in on some areas of particular interest in the phenomenal behavior of the problem. And then finally we're back to this finished solution, converged nicely, relatively accurate, all handled automatically for me by the software. So this is something you want to keep in mind as you're solving stress solutions. The same H-adaptive technique is valid for a modal analysis or a thermal analysis and a variety of other analysis types in mechanical. So keep this in mind as you use the software, and I hope you'll stop back for another interesting video in the future.